So we will be using the same San Francisco data, air traffic data, for doing time series analysis. Time series analysis or forecasting date with time variable plays a critical role. In time series analysis or forecasting, date or date with time. Sometimes you will see date with time, hours, minutes, and seconds. So there the date with time will become very, very critical role. Time variable is must time series forecasting. So we use this for forecasting or predicting the future. We use it for forecasting or predicting for future. There are two types of time series. Univariate time series, only two variables will be there. One date or date time, a variable y. In univariate time series, you will have only two variables. In univariate time series, you have only two variables, date or date time and y. Y is a numeric, y will be a numeric variable. Multivariate for time series, extracted and other independent variables. So in a multivariate time series, you will also have, you will extract variables from date, weekday, whether it is Sunday, Monday, Tuesday, or what day it is, what month it is, what quarter it is, whether it is a holiday, what season it is. All these things can be extracted, and there will be also other independent variables. In multivariate time series, regression models are used. There is one more type of time series called panel data. Panel data will have ID column and other independent variables, and panel data regression techniques are used. So one more time series data will be there called panel data. There you have ID column. ID can be a country or a company or something will be there along with date, and then you have other independent variables, and then you will run panel data regression techniques. There are some different techniques called panel data regression techniques, which will be implemented on that data. First, we will work on univariate time series forecasting. SF data, or let us say TS underscore DF is equal to SF data double square bracket. So TS DF underscore info. Now, as you can see here, we have two problems. Activity period is taken as int 64. Passenger count is taken as, okay, passenger count is okay, int 64. So activity period, we have to convert it into date. Activity period, we have to convert it into date. But converting it to date, there is no delimiter. There has to be a delimiter, right? Slash or hyphen. Hyphen or slash has to be there. Invalid syntax. String square bracket. So we will first convert the data to string. So first convert the San Francisco data activity period into string. Then we will insert hyphen. So this is the column 4 means 0, 1, 2, 3, 4. And then hyphen and then 4 column. Date has to have a delimiter. Either it has to be hyphen or slash, or it has to be number. Yeah, date and time variables are very important. So data, see, in typical any data, time will be there. So you have to look at the date. If it is not formatted, you have to format the dates, and accordingly we have to work upon it. Stock market data, sales data, every data will have time or date variable. Maintenance data, so dates will be always there in any typical data. Typically, we extract information and then we delete the date variable, but here date cannot be deleted. It has to be part of your analysis. Yes, name of the column. The starting point will be the name of the column. When you're changing the column, you should give name of the column, right? Dates have only hyphen and slash. Only two delimiters are ever allowed in dates, hyphen and slash. That to what slash? I have run this also. Now, after this, I ran the cell. After converting it into date time, then I ran the cell. Then you can see, right? Date time 64. After this, I ran the cell. See 21 and 22. See the cell numbers. I ran 21 and then I ran 22 again. Look at the cell numbers, you will get to know. Percentage capital M. Percentage capital M is for 3-letter words. Check PD date time function, you will know what is percentage small y is 2-digit year. Percentage capital Y is 4-digit year. Percentage small m is 2-digit month. Percentage capital M is 3-letter month. You can find it in date time documentation. What is the formats you have? All right. Converted into date time. Here is the same San Francisco data. Re-import the data here. Just re-import it again. Then you have to run this command first. Now we will create an univariate time series. TS underscore DF dot. Now we have to resample the data of quarterly, even hourly. So we have to resample data to a specific. In our case, the data is monthly data. So we will resample the data into monthly. So TS underscore DF dot resample, single quotes or double quotes, capital M, comma, on is equal to total monthly. TSDF monthly dot add. Now you can see here, date is indexed into rows. One of the important thing in time series is date is indexed. Typically, we have row numbers here, right? 0, 1, 2, 3, like that, we'll have row numbers. But once you format the data, see here, typically you'll have row numbers. But once you convert the data into a time series data, the index will be the date. Row numbers will be removed and dates will be 31st July, 31st August, 30th September. You can see this is the monthly data. And the date will be indexed into rows. Dates will be automatically indexed into rows. Once the date is indexed into rows, the data will be treated as time series. The data will be treated as time series data. Even in R also, dates have to be indexed into rows. Then only it will be there. Indexing in rows will, see, the algorithms use date as an index. In the algorithms which we are going to use, index is very important. That is why we are putting it into index. The algorithm was written in such a way that index is taken as the independent variable. Now, time series data is visualized as a line plot. Time series data will be visualized as a, so TS DF monthly dot plot. You can see the time series plot. In univariate forecasting, in univariate time series forecasting, one of the critical assumption is data must be stationary. Stationary means constant mean and constant autocorrelation. The assumption is time will not affect on, so data must be stationary. Data must be, if data is not stationary, you can see the graphs will be in red color. If the data is in stationary, you can see it will be in green color. Year and month, this will be fourth column. That is column 4. I've taken wrong format for data. Autocorrelation, correlation and lagged values of, autocorrelation is correlation between Y and lagged values of Y. What the hell? Why is it causing so much of problem? Let us say our Y is 1, 2, 3, 4, 5, 6, 7, 8, lag 1, lag 2. So data has to be stationary. Does our data look like stationary? Similarly, actually what happens is we can't make it out from our, so we have a test for stationarity. Augmented Dickey-Fuller test of stationary. I don't know why this thing is getting hotter. Okay. Augmented Dickey-Fuller test of stationary. The null hypothesis is unit root present, data is not stationary. The alternate hypothesis is no unit root or data is, the augmented Dickey-Fuller test will tell you whether the data is stationary or not. The interpretation is based on p-value. P-value less than 0.05, we will reject the p-value greater than 0.05, fail to reject the augmented Dickey-Fuller test of stationarity. From stats models dot TSA AD Fuller, so marginally our data is p-value is equal to slightly greater than, right? Fail to reject null. Chemistry is getting heated up. Now, if the data is not stationary, discrete differencing must be done. Discrete differencing must be done. Underscore date is equal to df monthly dot diff. PS df is equal to NA. The first observation will be NA. We are dropping it. If the data is not stationary, we need to do discrete differencing. Now, once you have done the differencing, how the data looks like. Now you can see here, the data looks like, this is the difference data. Now we will do the AD Fuller test again. Now the p-value is less than 0.05. Yes, only discrete differencing can be done. Your time series forecasting will fail. Stationary is a hypothetical situation. Data will always be non-stationary. Unit root means there is correlation or autocorrelation between the observations. For any hypothesis testing, p value is the only thing we will consider. Decomposition of time series. Breaking time series into components. One is or horizontal, seasonality based on 4 seasons, cyclicality, business cycle, and the fourth one, y minus lag of y. So business cycles are long-term trend, which is not visible in our short-term graph. So these are the stages in a business cycle, which is a long-term trend, 8 to 12 years. 8 to 12 years is a long-term trend for a business cycle. So we don't put it in it is not shown in the plot of the decomposition, but it is used in the calculation of decomposition. Expansion, peak, recession, depression, trough, recovery, again expansion and all. So this cycle to this cycle, it will take 8 to 12 years across the globe, depending on country. Decomposition of time series, we have Alt-Winters method of decomposition. Alt-Winters method of decomposition. First one is the additive model for non-seasonal data. YT is equal to trend T plus seasonality T plus cyclicality T plus error. Multiplicative model, which is suggested for seasonal data. YT is equal to trend T multiplied by seasonal T multiplied by cyclicality T multiplied by error T. So decomposition of time series. Stats models dot PSA dot seasonal underscore decompose. Seasonal underscore decompose. So you can see the trend is stagnating. You can see the trend is stagnating. Seasonal and residual. So there is a seasonality in data because you can see there is a perfect pattern repeating. There is a pattern that is repeating, which is indicating it is a seasonal data. Univariate time series forecasting. In univariate time series forecasting, the most popular model is PDQ. Auto-regressive integrated is a multiple two sets of equations. Auto-regressive integrated moving average is a multiple linear regression model with two sets of PDQ are the lags to be defined that range from 0, 0 till 5, 2, so PDQ are the lags which you need to define, and the range of these lags is from 0, 0, 0 to 5, 2, 5. That means differencing is only 2. D is your differencing, which will be only 2. First order differencing and second order differencing. 0 to 5 is your P lag and Q lag. Auto-regressive AR terms of P is multiple linear relationship lagged values. It is positive terms. This will be positive integrated, represented by differencing that is done on data. Moving average multiple linear relationship. This is negative. So ARIMA PDQ non-seasonal data PDQ PD and the time frequency. So for non-seasonal data, we will get only 3 ARIMA PDQ or SARIMA PDQ. For seasonal data, you will get additional parameters, the seasonal parameters. These are called as seasonal parameters. Seasonal parameters, additional PDQs will come, and time frequency. If you get SARIMA PDQ, it is non-seasonal model. If you get SARIMA, 2 sets of PDQ and frequency, it becomes a seasonal model. So this is the equation. YT is equal to intercept plus the AR terms, lagged values of Y, and the MA terms, lagged values of errors. 2 equations will be there. So ARIMA is a set of 2 equations. One equation representing AR terms, second equation representing the MA terms. ACF plot, auto correlation plot, which is the lag. So you will get a plots like this. Once you plot, you get a plot like this. ACF and PACF plots will look like this. Now, the interpretation is based on, both of them will start with lag 0. वो नहीं होगा बोल रहे थे. I checked with one of my friend in Kotak. He said it will not be done. नहीं आप ऐसे ही बोलोगे बाद में नहीं होगा तो इट इज अ प्रॉब्लम फॉर मी ऑन दैट. मैं देखता हूँ 1 मिनट. मैं कॉल करता हूँ आप. Okay. See, once you get the plot, you look for the point at which there is a big change. This is zero lag. You will ignore the zero lag. After zero lag, the point at which there is a significant lag, and it should be above the blue line, blue shaded line. So this blue shaded line is confidence interval. The blue shaded part is a confidence interval. The first lollipop after the zero lollipop at which you can see the above this thing, this indicates lag 1. So you need to understand the what you call lags in this manner for autocorrelation and partial autocorrelations. You need to find the point at which there is a big difference and where it is above the blue shaded area. It should be above the blue shaded area. So let us plot the ACF and PACF plots. PACF plot, auto correlation plot, which is the lag, D is the differentiation. From stats models dot graphics dot PSA plots, plot underscore ACF, comma, plot underscore PACF. Plot underscore ACF, TS monthly date, comma, lags is equal to 30, max lags is equal to 30. So it can be 3. See, it's slightly above, right? Plot underscore PS here, I think both of them are suggesting 0 only because the other lags are within the shade. So we can't make it from the plots. We can't make it from the plots. In this case, we are not able to make any decision based on plots. So for that purpose, we have something called auto ARIMA. Pip install PMD ARIMA. Install this library. Pip install PMD ARIMA. Exclamation pip install PMD ARIMA. It is not out of the blue area, right? That's what, no, that is 2. This one. We don't go beyond 5 lakhs. If nothing is above the blue line afterwards, we will take the first one. Lag 0, we will ignore first. And then we look for other lags. If nothing is available, then no option, we have to go with lag 0 only. The lags will be between 0, 0 to 5 to 5. It cannot be beyond 5. 5P, 2D, 5Q. 5P, 2D, 5Q. Here, na, I'm giving you PDQ. Auto ARIMA, all combinations PDQ 00525 and identifies the lag order Akaikos information criterion, also called as AIC. So auto ARIMA will run all the combinations from 000 till 525 and identifies the lag order that has the least Akaikos information criterion. So this auto ARIMA function will help us a lot. When we can't decide the lags from the ACF and PACF plot, we will run. So PMD ARIMA, auto ARIMA will run the parameters right from P is equal to 2. So we have to give P is equal to 0 and max P is 5. Max D is 2. Max Q is 5. So we have to just give P is equal to 0 and Q is equal to 0. Start P and start Q, it starts from 2 only, but we will give it as 0. And then one more important thing is stationary is false. If you are giving difference data, we have to change stationary is equal to true. Or else we have to give undifferenced data. Undifferenced data, it will automatically calculate stationary. It will do the stationary test, and depending on that, it will do the differencing, and then it will implement the data. So auto ARIMA is a fully automated function within the PMD ARIMA, which will help us to run automatically and come up with the best lag order. That's why I think this would be 0. Or let us see what PMD ARIMA gives us. PMD ARIMA will give us the best possible lag. From PMD ARIMA dot ARIMA auto underscore ARIMA. Model is equal to auto underscore ARIMA TSDF monthly, comma, start underscore P is equal to 0, start underscore Q is equal to 0. I am giving the undifferenced data because we are assuming stationary is false. So it will do stationary test and bring the data to, see, 0, 1, 0. It has taken 0 lakhs only. 0, 1, 0. See, first order differencing. So it is taking 0 and 0 because none of the other lags are greater than top than blue thing, right? So obviously it has to take only 0 lag. First, we will ignore the 0 lag and then look for other lags below 5. If nothing is there, then we have to go back and take 0 lag only. That is what it has taken, 0, 1, 0. First order differencing we have to do to bring the data to stationary. So you can see here, it has built ARIMA model 0, 1, 0. ARIMA model 0, 1, 0, non-seasonal data. If there is seasonal parameters, you will get additional parameters here. So we didn't get additional parameters means not a seasonal data. And you can see Akaikas information is 5798.765. So auto ARIMA is a function that helps us to find the best possible lags. Separate 3 more parameters will be there. And in square bracket, time frequency of the data will be there. Like your monthly data, na? So 12, frequency will be 12. If it is quarterly, it will be 4. If it is annual, 1. D is none. So it will automatically start with 0 only, right? And then max is differencing cannot be second order differencing. We can't go beyond second order differencing. First order differencing is most of the time 0. So it will start with 0 only. Look at the documentation of PMD auto ARIMA, you will see a lot of information is there. The lung box test of, then we did the prediction, then we are plotting the predictions.